So let me also start by thanking everybody here at ITAMP for organizing this nice, not workshop, but what is it, reunion. And more than that, also let me start by thanking ITAMP for having me and giving me a fantastic time here. And, you know, like not only always having a reliable crowd around for some soccer, but also having Fabian as kind of an unofficial ITAMP fellow, then also having our dressing cloud of Mariella, Hossein always being super welcoming, and I don't know what he's like teaching right here, like what he's going on here. But also hosting our students repeatedly and really making things work for us in somewhat complicated settings. So thank you, Hossein, and everybody at ITAMP for that. Okay, so now let me start by telling you a bit about what we are currently working on by trying to simulate really hard, strongly correlated quantum many-body systems by combining what we can get out of quantum simulation experiments and machine learning, and in particular neural networks. So okay, we know all of these different platforms, you know, for quantum simulation, like trapped ions, Rydberg tweezer arrays with atoms and optical lattices, and so on. And what I want to tell you about today is how we can use data that comes out of these experiments in combination with neural networks to should I move my microphone?
Sorry.
Because we don't use it for it's for online work.
Perfect. Okay. That's better. Good. Okay. Yes, so what I want to tell you about is how to combine data that we get out of these quantum simulation experiments with neural networks to basically get the best of both worlds. But of course, we have to start with like one of them. I think quantum simulation is something that most of you are familiar with. So I want to really tell you about the machine learning or neural network part. And here the idea is basically something that Giuseppe Caleo put forward a couple of years ago to use a neural network. So in this case, this is somewhat the simplest thing that you can think of is a restricted Boltzmann machine. And we now use this neural network as a variational quantum state. So the idea is that you can put in any configuration and the network will tell you what the wave function coefficient for that configuration is. So it's very similar to, for example, what you would do with matrix product states. The idea being that you can use a neural network which presumably might have a higher representational power. And in particular, people have shown that things that you can represent with matrix product states, you can typically also represent with these neural networks, but you can do more with the neural network. So the hope is that basically by using now a neural network and with all the machinery that the machine learning community has developed in this regards, we can basically simulate more and hopefully in particular two-dimensional quantum many-body systems here. Okay, and so there's a lot of different things that you can do, for example, different neural network architectures that you can use. So for example, a simple feed-forward neural network or convolutional neural networks or more complicated things that you can use here. But if you don't care so much about the technicalities of neural networks, you can really view it like a black box, where you say you input your configuration, for example, like your spin configuration that you're interested in, and the neural network will output you the wave function coefficient of that. So okay, that's really the kind of main gist of the neural network quantum states idea. And there's different things that you can now do with these neural network quantum states. So I think the maybe most obvious and the first thing that people did was to find ground states, which means that you really just want to minimize the energy. So the thing that you are going to do is you want your neural network to represent the ground state of your system. And so you do the entire thing that people in the machine learning community would do, just the cost function that you train on. So what you really want your network to do is to reach an energy that's as low as possible. So your cost function will literally be to minimize the energy, so the expectation value of your Hamiltonian. But then, of course, there's other things that you can do. You can also do state reconstruction, where you get some data from, for example, a quantum simulation experiment, and now you tried your neural network to represent the state where this data comes from as best as possible. Other options are, for example, dynamics, so you can also simulate the time evolution of a quantum system, or finite temperature states. There's also, of course, open quantum systems, but I'm a bit scared of open systems, so that's not on here. Okay, and today I mainly want to talk about ground states and state reconstruction and how we can combine those things. So I will start by telling you a bit about the things that we've been doing to find ground states, in particular of two-dimensional quantum many-body systems. And then I will tell you a bit about what you can do to reconstruct a quantum state from data. And finally, we will combine both of these things together. Okay, so the first thing that we want to do is really just minimize the energy. So what we are going to do is we start randomly initialize our neural network, then we sample from it, from those samples. So this is really just variation in Monte Carlo with the add-on that our state is now represented by a neural network. So we sample and then we evaluate the energy or the energy gradient, and then based on the energy gradient, we update our neural network parameters such that we get a better expectation value of our energy, and we keep doing that until at some point our energy gets as low as possible, hopefully. And of course, this is in terms of ground state search, this is nice because you just know you always want to go lower and lower in energy. So that's a somewhat obvious target. Okay, and there are some examples from the literature which make me quite optimistic that this is a promising technique to use. So here, for example, this is a result for the 10 by 10 Heisenberg model. In the same paper, they also, so this is from a year ago, they also looked at the J1, J2 model, and they reached the lowest energies to that date for the J1, J2 model on, I think, like a 10 by 10 system also. So here, typically, what we're looking at is the relative error of the energy. And here, they plotted as a number of parameters, so the 3 parameters that they use. And you can see that with their CNN, so their convolutional neural network, they reach really, really low energies. And this plot is maybe even more interesting because here they're looking at a triangular lattice, so again a spin-1/2 model, and now they compare the energy that they get with the energy that you get out of the MRG. And the nice thing here is, you're looking for the ground state, so you just want to go as low as possible. And if your neural network gives you an energy that's lower than what you get out of the MRG, you're doing better. And that's exactly what happens at some point. So they are plotting this difference between the neural network and the DMRG energy as a function of system size. So this is a 6x6, 8x8, and so on system. And you can see that for the smaller systems, even though all of them are quite big already, the DMRG gives you the better energy, so this difference is positive. But then once you start going to really big systems, like 14 by 14 or 16 by 16, the energy that you get out of your neural quantum states becomes lower. And so there's a couple of examples like this where we see just empirically that these neural networks can outperform what we have with other methods. And so most people look at spin systems, spin-1/2 systems, but what I, of course, care deeply about is more TJ or Fermi-Hubbard type models. So we started saying, okay, why restrict ourselves to a local Hilbert space dimension of 2? Why not just go to a local Hilbert space dimension of 3? And also start thinking about fermions, right? Because one big picture motivation is that ultimately what we would like to look at is like two-dimensional fermionic systems here. So we looked at this TJ Hamiltonian, and basically the typical procedure that you get looks like this. So you look at the energy here. We are doing small systems to be able to compare to exact diagonalization, so we can evaluate the energy error and know how well we are doing. And then as a function of your training steps, you nicely see how this energy goes down over time. And the nice thing with the neural networks is that you have a cost function, and you can add now whatever you want to that cost function. So for example, what we did here is to add a momentum constraint. So typically we would have our energy as a function of momentum, but our cost function just gives us the global minimum, so the minimum over all momentum states in energy. But now if we say, okay, we want to really map out this dispersion, so we want to find the ground state within a given momentum sector, for a neural network quantum state, I can add whatever I want to the cost function. So I basically can change my cost function, which here would just be the energy, and in that cost function write a term like a Lagrange multiplier, forcing us into the right momentum sector, and thereby changing this loss landscape and giving me a new minimum. And thereby, basically, even though the energy is higher, but my momentum is at the target momentum. And with that method, we can, for example, map out the dispersion relation. And this is something that's quite hard to do with other methods. So you can also do this, for example, with matrix product states, but it's a bit of a pain to really do this, whereas here, it really comes at the cost of a ground state search. And you can see that this works fairly nicely for example, this TJ model. So this is a comparison to exact diagonalization calculation. And you see that you really nicely capture this dispersion relation. And The nice thing is now you can also go to larger systems. So this is now for a, I think, 4x20 system. The color map that you see is a matrix product state calculation that I did during my PhD, and where you have to really do a full time evolution and Fourier transform it, get the spectral function, get the dispersion out of this. And these symbols here are Hanna's ground state calculations, where you basically just at the cost of a ground state calculation can now map out the same dispersion relation. And the nice thing is also that we now went from 4x4 to 4x20, I think, and it's not that much harder. So that makes me quite optimistic in principle that we can really go to larger systems here. One thing that's quite interesting, this was for a single hole. So now if we put more holes into the system, we have to start caring about whether this is fermionic or bosonic. And it turns out that this becomes harder, right? So if you don't have any holes in your system, so this is the blue curve, then you nicely go down. But as soon as you start putting holes into your system, there are some cases where the convergence is not so great and you seem to get stuck somewhere. And this is really an optimization problem. So because this is looking at, again, fairly small systems. So here we know we can put as many neural network parameters as our Hilbert space dimension, but still sometimes we just get stuck in these minima and we cannot find out. And this is somewhat a disadvantage compared to something like DMRG, where you know you have this very efficient optimization algorithm to find your ground state. Whereas here, it just happens that your loss landscape doesn't look so great. You get stuck somewhere. And of course, here we compare to exact diagonalization or matrix product states. But in the interesting cases, you wouldn't have this point of comparison. And then you're just stuck somewhere. And that's not so nice. OK. One more example for ground state search is this is a bosonic system, so a bosonic Hofstadter-Hubbard model. And here we are looking at really long-range interactions with a large blockade radius. So this goes to show that we can really do large systems also with long-range interactions. So for example, 12x12 systems. And we find these, we find different nice phases here where you see these like kind of bubble crystals emerging and so on. And the nice thing is here that this is something that starts to get really challenging for matrix product states, right? Because it's a large two-dimensional system with very long-range interactions. But this is still very much doable with these neural quantum states. So overall, the message from this part is there's a lot of things that are doable, but there is the danger that your optimization becomes very difficult with these neural quantum states. Okay, so the second thing that I wanted to tell you about is quantum state reconstruction. So that means that now, instead of searching for the ground state of a Hamiltonian, you have data from, for example, an experiment, and you try to get your neural network to represent the quantum state from which this data originally came. And this is something that has been done. So, for example, the group of Roger Melko did this with experimental data from Misha's group. So here, for example, they use a restricted Boltzmann machine. They actually add an additional noise layer to account for some, I think, detection errors or so. And then they basically put in the data from the experiment, and they really want their neural network, so this restricted Boltzmann machine up here, to represent the same probability distribution from which this data originally came. Okay, in a way you can see this. You have a data set here. You have your neural quantum state. The data set has some distribution Q of sigma, so each configuration sigma appears with a certain probability. The NQS represents a different probability distribution to begin with, and what you're going to minimize is this Kullback-Leibler divergence, which basically gives you a measure for the distance between these two probability distributions. So you're trying to minimize the distance between these distributions such that your neural network approaches the original data distribution as closely as possible. And you may wonder why you would want to do that. But one thing is that, for example, you can now, from this neural network quantum state, you can start to evaluate quantities that you cannot get so easily out of the experimental data directly. And you're basically doing an efficient job at interpolating between the samples that you are seeing. So it turns out that to evaluate certain things, so in this work that Roger Melko, for example, did, they saw that you can now evaluate things in different bases that you actually didn't measure in the experiment fairly nicely. This is, of course, now when I talk about probability distributions, this is only thinking about measuring in the computational basis. So if you have a state like this, then you sample a snapshot like that, you sample a snapshot like that, and then you basically, this gives you a probability distribution over these snapshots, but you don't have any phase information. So imagine, for example, you just have a singlet state, you have a minus between these configurations. By just learning the amplitude, so the probability with which these configurations appear, you don't learn anything about the phase between those states. So if you want to learn something about the phase between the states, you actually have to measure in different bases somehow. So it's not enough to just measure in the computational basis, but you have to do some basis rotations in the experiment. So that's one thing that you have to do, but also on your neural network quantum state. And that turns out to be also not as easy as one might think. So we will get back to that later. Okay, so this was the quantum state reconstruction to just give you an idea. And now I want to combine the quantum state reconstruction with the variational Monte Carlo part. So basically now we, instead of starting from a random initialization of our neural network parameters, we start by training on this experimental data to get a representation that's as good as possible, like approximating the experimental data. And then we start our variational Monte Carlo from that state. And what this basically does is it puts us into a much, much better position in our loss landscape. So instead of just randomly starting anywhere, we use the experimental data to really put us sort of in a prime position to then do the energy optimization in the second step. And maybe in a nutshell, the message from this part is that even if your experimental data isn't perfect, so even if there is defects, or maybe it's like a finite temperature or so on, then still this helps you a lot in terms of converging to the actual ground state in the second part when you train on the Hamiltonian. Okay, so first part of this was done with Skylar from Roger Melko's group, and we used Misha's experimental data here. So I mean, I think you're all familiar with the Hamiltonian of these Rydberg tweezer arrays. And there has been, of course, a lot of experimental data mapping out this phase diagram here and so on. And we were like, okay, we can just reuse the data that's existent and train our neural network on that. And so again, this is a two-dimensional system. Here, in this particular case, we don't have any phase information. So that's actually a nice case to start. So we don't need this part about measuring different bases and so on. Really, all the information is contained in these measurements in the computational basis. And so what you see here now is the expectation value of our energy, represented by the neural quantum state, as a function of the training steps. And you see three different curves. So this says 1D because the network architecture is a 1D architecture, not a 2D architecture, which means that the architecture is not as powerful as it could be for this two-dimensional problem. And okay, so the first thing that you can do is forget about the data, just initialize randomly and do variational Monte Carlo. And this gives you this blue curve here. So this gives you this energy up here. And that's pretty bad because we want to go down to this black dashed line. So just doing variational Monte Carlo is not so great. The other thing that you can do is to just train on the data. And that's the orange curve. So if we just train on the data, it's actually nice. We get a much lower energy already just by training on the data, which also shows you that you are fairly close really to the ground state with this experimental data. But you still end up here. And now the third thing that we do is the green curve, where we basically do the same thing as in the orange curve, so training on the data, representing the experimental state as good as possible up to this red dashed line. And then at the red dashed line, we switch to now training on the Hamiltonian and minimizing the energy. And you see that we now get a lower energy than both of these things do. And I think this is really pretty amazing because you sort of combine two things that are not great. So the variation of Monte Carlo in itself is really stuck somewhere up here. The experimental data is good, but it's really also not giving you quite a ground state energy. But now if you combine these two things, you get a significantly lower energy and come to a really better state over there. Okay, and now you can also do this for a somewhat better architecture, which is a 2D system. And there you see that you, anyway, so even without the data, you would reach a pretty good ground state energy, but you do so much faster if you train on data. So if you compare the green, which is this hybrid approach where you first train on data and then on the Hamiltonian with just training on the Hamiltonian, and you see that you reach your energy much faster. So you basically have to do much less training, which is also nice because, I mean, training this uses up computational resources, right? And you can do this now. So Misha has a lot of data, so you can do this now for a lot of Hamiltonian parameters, so basically going through your phase diagram. But what we see consistently is that this green line, so this hybrid approach, always does as good or better than either the data or the variational Monte Carlo. So basically, it's always better to initialize your state with data if there is any data available, and then do variational Monte Carlo instead of like either just using the data or just using the Hamiltonian here. And you can also, for example, look at observables, and the same thing holds true here. So if you do, for example, the staggered magnetization or the expectation value of sigma x, in all of these cases, you see that you do much better if you do the hybrid approach. Also compared to, for example, the experimental data, which is down here, and variation Monte Carlo, which is down here, which is really bad. And we know what it should look like is this actually quantum Monte Carlo simulation, which are these red dots that you hardly see. And you see that both of these approaches are really, really far away. But if you combine the two of them, you really get a pretty good result. So up here, you get a spot-on solution for that. So that's very nice. But in a way, you see that here we are still comparing to quantum Monte Carlo. So it's not yet the hardest problem we could be looking at. And so we now are looking at a somewhat more complicated system where you also, or some of them where you also have some sign structure. So you also have information beyond just the computational basis. And there's two things that we are now doing differently. And I think most important part is that we now are able to train in two different bases. And we kind of take the same approach as before. So we do first training on the experimental data, and then we switch to variational Monte Carlo, with the main difference that here in this part where we train on the experimental data, we only not only use information from the SZ basis, but also from the SX basis. And the second thing that we do that's a bit more of a technicality is that we now use an even more powerful neural network architecture, which is this transformer architecture that you might have heard of in the context of ChatGPT and these large language models. And this is what we are now using, with the idea, of course, being that if you want to really represent any long-range correlations and so on, that this might be a really good approach to choose such an architecture here. Okay, and so maybe the first example that we're looking at is just a 2D transverse field Ising model. And again, so now there's an additional curve, right? Because we can do now just the variation Monte Carlo, so just training on the Hamiltonian. We can do the hybrid learning where we just train in the Z basis. And we can do the hybrid training where we just train in the X basis. Or we can do the hybrid where we train in both the Z and the X basis. And so this is a bit of an involved plot, but you see as we scan our transverse field in the transverse field Ising model that the variation Monte Carlo, just doing the variation Monte Carlo, always gives us a pretty long convergence time. So this is the convergence time here. Whereas any hybrid approach, either just the Z basis or just the X basis or both of them, always give you a significantly lower convergence time. So this is, in terms of computational resources, this is really good. And I should say, I mean, we have like a very limited amount of GPUs available to do this. So this is actually a factor right now that matters for us. If you can do it in like half the time or like a third of the time, that really makes a difference for simulating systems. But then we also find that there is regimes where you really need, or you really do better if you have the information from both bases. So in particular here, for this small transverse field, you really do better if you look at information not only from the Z or only from the X basis, but if you combine this information and you really not just get information about the amplitude, but also about the phase structure of your state here. And the other thing that we've been looking at is data from the Paris group. So they realized this this XY model with this 1 over R cubed interaction here. And this is something, so they also do a RAM to prepare something that's as close as possible to the ground state of this Hamiltonian. And the main part here is that you cannot so easily do quantum Monte Carlo because you have this phase information. And for certain system sizes, you can still do DMRG, which actually works surprisingly well, but that's also something that really is hard to get to converge. And here, so I showed you already some of the energies. The other thing that we can look at is now observables, like for example, correlation functions like SX or SC correlation functions. And here the message is somewhat the same as before. You have the experimental data, which is down here, the DMRG, which for these, I think this is like a 6x6 or 7x7 system. So the DMRG tells you more or less the exact result. And so that's up here. So you can see that the experimental data is somewhat not spot on with what it should be, right? So you are not preparing really the exact ground state in the experiment. You're getting something that's close to the ground state, but it's definitely not perfect. And the same here for this SC correlation functions. And then you can use your transformer neural quantum state and do variational Monte Carlo only, and you get the gray line. So you're doing, I would say, somewhat better than the experiment, but still it's not that great. But now if you combine these two things, so you combine your neural quantum state with the experimental data, you really come extremely close to what it should be, and you get a much better result than each of them. And I find this really amazing because you take this experimental data, which is sort of even further away from the true solution than your variational Monte Carlo is, but still in terms of the loss landscape of your neuroquantum state in which you try to train, this puts you somehow into a so much better spot that you then reach a really much closer approximation of your ground state. Okay, and maybe the last thing I want to show you is somewhat the power of these neuroquantum states in terms of the number of parameters, because we always want to compare this to established methods. And one of them is, of course, matrix product states. And it's a bit hard to compare, say, the runtime, because the matrix product states are optimized on CPUs, and there's a lot of the CPUs. The neuroquantum states are optimized on the GPUs, and how do you really compare the runtime? But what you can compare is the number of parameters that you use in your variational quantum state. And here, so the different colors are different parameters in your Hamiltonian now. So you can look at, just focus on one of the lines, for example, the yellow one. And we're looking at the energy, or like the energy difference to the DMRG result for a very large bond dimension as a function of the number of parameters. And our transformer, so our neuroquantum state, sits over here. So you see that we are, in terms of parameters, we are something on the order of 10 to the 5. Whereas our matrix product states, the one that give us like an equivalent energy would be like a bond dimension of something like 500 or so, which has like 2 orders of magnitude more parameters that we use in this ansatz. So that tells you how powerful these neuroquantum states are in terms of representing your quantum many-body state. You can do with a lot less free parameters to get the same kind of approximation to ground state. And now, of course, the problem is that you need to find that representation. So you need to somehow get there in your loss landscape. And that's where we really have a big advantage by using this data from quantum simulation experiments. So I think there's really a good prospect of combining more of this data also for different systems with these neuroquantum states in this hybrid approach. I hope also for fermionic systems soon to really get even better ground state energies for 2-dimensional systems. Okay, let me maybe skip over this outlook here and just thank you for your attention.
Thanks a lot for the talk. Couple of questions.
So you said that the transformer model performs so much better than like the simpler neural networks. Can you say a bit more about like how you choose the type of neural network that you want to use, and is that in any way related to the types of states you want to represent or the models you want to simulate? Yeah,
that's a very good question. I would say that's a thing that's very much up to debate in this neuroquantum state community. So that's something that's not really known. So beforehand, what we used in the first part were recurrent neural networks, and they somewhat intrinsically have more of a one-dimensional structure. So I think for 1D systems, they are a good choice. For 2D systems, you can basically change the architecture such that it represents a 2-dimensional system, but the transformer is more natural in doing so because it uses something that's called the attention mechanism, which basically allows you to have like arbitrary correlations throughout the system without having to do something. So for example, one other choice would be a convolutional neural network, which is what's typically used to analyze images. And there you typically have a filter of some finite size that you go through your system. And in a way that's nice because you automatically include translational invariance because you say, I take the same filter and move it throughout my entire system. But on the other hand, naturally this looks at then correlations on a somewhat small scale, like on the size of your filter, which would be like 3 by 3 or 4 by 4 or something like that. But if you're saying, okay, I really care about some long-range properties in the system, then it might be that something like a transformer where through this attention mechanism you can naturally include that is a better choice. But a priori, I would say this is not so clear what you should do, and there's like different disadvantages and advantages of the different architectures. Mm-hmm.
Thanks for the really nice talk. I have a related question, maybe. So you mentioned at some point, and there are interesting phases which you can see. There was a plot in the upper right somewhere. And I'm wondering, if you look at these systems, you want to learn about, let's say, different physical phases and how the robustness and new effects. And then the question is, how much does it help me to try to beat the ground state energy and get a better energy? And when you say attention mechanism, to actually see that, usually you try to represent things via effective theories. And can you see fingerprints of effective theories represent, you mentioned I need less parameters. For the BCS theory, I need probably 2 or 3 parameters, and that's it. And I get very good results. Is there something hidden in neural networks of that spirit? That is question 1. And question 2, is there a relation to finding a new DFT functional by optimizing the cost function?
Okay. So regarding question number 1, I think that's an excellent question. It basically boils down to interpretability, right? What can you learn from your neural network architecture? And there's some ongoing efforts of what you can learn from your architecture. So one thing that we are looking at with, like one of my students, is to impose more symmetries into the state so that you can directly say, for example, you impose all of the spatial symmetries and so on, that your network directly incorporates those. Another thing that we're trying to figure out is, can you do something where your network takes only correlations up to a certain order into account in representing the state, and then okay, I don't need to go beyond second order correlations, so it's probably a fairly simple state and so on. But it's something that doesn't come so naturally to really gain interpretability. And you mentioned the attention mechanism, so that's something that I think for physicists, we always think, that must be the natural way to interpret it, because it's literally that this attention mechanism tells you how one side or one patch in this patch transformer cares about another patch, and so you feel like I should be able to just look at it and get an answer. But unfortunately, it turns out to be not quite as easy. So if you look at it, it's somewhat useless. And the second question, I have no idea.
You did optimize the energy of a fermionic system. It sounds very much like what we do in DFT, where we try to search for new functionals. And the question is that somehow related, the search for good cost function, and to optimize? You could extract the band structure that we also do in DFT. We have functionals where we can go to find a momentum. Then, is there some relation of finding DFT functionals and neural networks?
I think there is exactly one theorem proved about transformers, one micro theorem in total.
Yes, yeah, so I don't know of any connection, but I mean, it sounds interesting. And honestly, like what Misha says, so what people here do is they try it out, right? So it's really trial and error.
Okay, so I think we have to close the first session. So let's thank Annabelle and